Assalamu alaikum everyone. This is chapter 10, frequency response techniques. This is an alternative approach to root locus. In the root locus, we varied the gain. We have the graphical method to figure out transient behavior, stability information, and we also designed the control system based on that graphical technique, and we have introduced compensators that are going to reshape the location of the pole. That means reshaping the root locus. So this is all we discussed in chapter 8 and 9 in detail. Actually, we took too much time to understand the graphical method that actually helped us to have better understanding of control system design. So this is an alternative approach, the frequency response techniques. Actually, the design based on the frequency response techniques will be followed in chapter 11. So we have to go a bit quick on this chapter. That is why we're going on slides. So if you have any confusion or question, you're always encouraged to ask whenever you want. Okay, so let's start. Now, why this frequency response technique? One of the first disadvantage of the frequency response technique is that it is very old. It was actually invented before the root locus techniques. And still we are going for that. So what are the advantages? First of all, if you have to model a transfer function from the physical data, you don't have any physical system information, but you just have the data. Based on that, you have to model the transfer function. Then this is one of the easiest alternative to go for the frequency response technique. Also, it helps us to design lead compensator to meet both the steady state error requirements as well as transient response requirement. Also, it is helpful while you want to find out the stability of the nonlinear system. So nonlinear system, in the root locus, you cannot go, but here, if you have the diagrams, frequency response diagrams, you can actually figure out the stability of the nonlinear systems as well. Okay, also the points where it is difficult to go for the root locus method, actually, we can also go for the frequency response techniques. So the basic fundamental of the frequency response technique is that if it is a linear system and you are applying a sinusoidal input to the linear system, then it will always give us another sinusoidal signal of the same frequency. So frequency will be remaining same. So this is the bottom line. What will be different is the magnitude can be higher or lower, okay, as well as the phase angle will be different. Okay, so which is clearly seen from here. So if this is your input and if you have a magnitude of mi and you have a phase of phi I, then what we can get from the output is output magnitude will be m0 and output phi is phi 0. So our system, which is actually giving the system transfer function, will give you m omega and phi omega. So this is the behavior of the system. So if you multiply input with the system transfer function, both represented in the phasor, then you can go, if you just multiply these two, then you're going to get this one. Okay, so this is what is been shown here. So as you know, the magnitude will be multiplied together. Okay, so magnitude will be multiplied together, angle will be divided. So now if you are interested actually how to represent our system, so we are actually interested about the m omega and your phi omega. Okay, so phi omega we want to figure out in these two. So if you just divide this one by the output by input, then you're going to find out the magnitude. then you're going to find out the magnitude of the system, as well as the angle is divided is actually subtracted. So if you just find out subtract the input phase from the output phase, then you're going to find out the phase of the system. Very basic idea. Okay. So now analytically, what is actually represented by, what is mean by the frequency response? Analytically means actually mathematically what we can find out what is a frequency response. So for that, as you can see here is actually for a particular system G of S, we are applying the input, okay? So which will actually give us the forced response. And the input is, we're just assuming that A cos theta plus B sine theta, and which can be represented in a phasor form like this. The magnitude is root over A square plus B square, then cos omega t minus tan inverse B by A. So this input can be represented in one of the three ways. The first way is the polar form. So angle and angle and phi. So as you can see here, you have a negative sign, but they are not showing the negative sign here. They inserted the negative sign here. So it's actually better to represent that tan inverse beta by A is actually phi. Phi equal to tan inverse B by A. Okay, then we can assume to be in line with the derivation of the book, that we can assume that phi I is actually minus phi. So it will be same then. Okay, so you can represent in the polar form. Okay, so this is the ambiguity of the book, so we can resolve that. So if you take the minus sign here, okay, so cos basically magnitude and the minus angle, then it will give you a minus in JB. And also you can represent it in terms of magnitude e to the power j minus j phi I. So, but if you are actually interested about representing in actual quantities for this one, not in the notation, that it will have to be root over a square plus b square, then you have e to the power j minus j phi. So phi is already, you have seen what is phi. Okay, so now what will be output? Output is simple. Output is input into the system transfer function, that is G of S. So we already know what is our input in the Laplace domain. So it has two root at minus j omega, at plus j omega. So we have two partial fraction of the input, as well as we have to find out the partial fraction of the G of S. But we are not that interested about the partial fraction of the G of S, because if the system is stable, then that will be eventually in the steady state effect, the G of S will have some root that will be minus sigma d, okay, sigma d plus j omega d, something like this. So basically, eventually they will be vanished. Okay, so because of the, so it may or may not have the oscillatory nature. So it can go like this, or it can directly vanish like this. So eventually, the bottom line is, for the steady state analysis, we are actually interested about the force response, that is the response of these two only. So this is going to be vanished. So what is K1 and K2? We know how to apply the, find out the coefficient of partial fraction. So do the same thing, and you're going to find out that the magnitude of A plus JB, magnitude of this one will be coming, which is the input magnitude, as well as the magnitude of this one. So magnitude of this one is represented as MI, and then you have the phasor angle e to the minus j phi I. So since phi I, that is why, because we know that phi is a minus of your phi. So this is just to have a similar derivation. Similarly, from this one, what you're going to get is the magnitude of this one, as well as the negative angle. Okay, so you'll have something like this. Similarly, you'll have values for K2, and eventually you're going to see that it is the magnitude is same, only the phase angle is have a negative angle. So this is the condition for your complex conjugate. So basically K2 is the complex conjugate of the K1. Okay, so now what is the magnitude? We can define the magnitude of the system. So the magnitude of the system is magnitude of the G of j omega, and phase angle is the phase angle of your G of j omega. For the steady state, we already said the transient, if it is a stable system, so the partial fractions of the G of j omega will be vanished. So we just have the forced response remaining. So we already find out the value of the K1 and K2. So we just put them together. Then we simplify a bit. And then what you are going to get is this. So basically, this is the input magnitude. This is your the system magnitude, and this is the phase angle. So basically, what we can define as our frequency response is whenever you are setting your S equal to j omega, then it is actually becoming your frequency response. And what is in real life, what I mean by that is actually whatever the system's behavior that you're trying to figure out is we are just considering from changing the value of j minus infinity to j plus infinity. Okay, so we are just finding out the value of g of j omega. Say you have a pole A0 and a pole, something like this in your system. So what you're trying to do is basically the idea that you have derived in the root locus, similar idea you're trying to apply here. So we are taking maybe this value. So it is enough to take one, because the other one will be definitely the their complex conjugate. So basically if you just draw from 0 to plus infinity, the 0 to minus infinity will be just a replica of that one. So at this point, what is the magnitude and the phase? You have to just multiply, find out the lengths of the zero lengths and the pole lengths. Then your pole length, zero lengths by the pole length will be your magnitude, and the angle contribution by all of them. So basically the same idea. So magnitude is nothing but the product of the zero lengths divided by the product of the pole lengths. And what about the phase? Phase is same. So summation of the zero angles minus summation of the pole angles. Okay, so nothing new. So if you want, what should be the magnitude here? So at any point here, so what you can do is you can draw the lines. Okay, then for magnitude, you have to find out the length of this magnitude. So whatever the zero length divided by the two pole lengths, and also the angle. So will be similar. So zero angle minus this two angle. So this is how you have to figure out for each and every point from 0 to j infinity. 0 to minus infinity or minus infinity 0 will be just replica of that one. Okay, so plotting the frequency response. So there is several ways to do it. So we are going to focus two means of plotting the frequency response. One is called separately, you have to draw the magnitude and the phase. Okay, so separate in two separate diagram. So magnitude will be in decibel versus log. So decibel is nothing but 20 log m. So whatever the magnitude we have to take 20 log of that one. So then you're going to get the magnitude. And the phase plot will be whatever the phase angle that we have, that in terms of your log magnitude. Because it is very difficult to plot in a normal graph, because we are traveling from 0 to infinity. Okay, so but if we go in the log graph, then actually you have exponential graph, so we can easily plot it. So that is why the frequency we have taken in a log curve. So this is one way to do it, and this is actually related to your board plot. So these are actually related to board plot. Okay. And the other ways to do it is by the polar plot. The polar plot, where you find out the phasor length, magnitude, and the angle, and correspondingly you just put the value in the phasor. So that will give you the polar plot. So basically, from the polar plot, we'll try to figure out the Nyquist criteria. Okay? So like part of it actually, Nyquist criteria or Nyquist diagram, you can also say Nyquist plot or Nyquist diagram. Okay, so let us start with a simple example. Okay, so the first step is very simple. First step is replace the GS S by actually J omega, then evaluate it, and then you have to figure out the plot. So in your example 10.1, the frequency response of the given transfer function you have to figure out. So your transfer function is this one, GS equal to the simple transfer function, GS equal to 1 by S plus 2. So first idea is very simple. S has to be replaced by, because you're just varying the value of frequency, so S has to be replaced by J omega. So you put the value and then simplify a bit. Then you're going to have a, because we generally don't keep the complex number in the denominator, so you multiply the complex conjugate, so you're going to find this form. And also from this one, you can find out what will be the magnitude. Magnitude will be actually root over 1 by root over omega square plus 4. So this is what we calculated. And what will be the phase? So since it is in the denominator, so whatever the phase, tan inverse omega by 2 is what we are going to get, tan inverse omega by 2. So since because it is in the denominator, a negative sign will be there. Simple. Now let us, we figure out what is the magnitude, we figure out what is the angle. Now we have to go for the plot. So in one, we actually are going to plot in both in the separate diagrams, or in the log diagrams, as well as in the polar diagrams. So let us try to do that. So in the frequency, the separate magnitude curve actually. So what you can see here is, so 20 magnitude we already figured out. So just replace the value of the magnitude here. Okay, so the 20 log, which is in the decibel, and then you figure out, yeah. So if your omega equal to 0, then you put the value, it will be actually half. So half, so 20 log 0.5 is actually, this is actually nothing but 0.3. So 0.3 into approximately 0.3. So 0.3 into 20 will give you -6. So that is where your curve is starting from -6. Okay. So gradually you increase the value, and correspondingly find out the value, you are going to have a curve like this. Similarly, the phase plot as well. So you can find out what will be the phase value. So the initial curve we started from 0.1. We could have also used started from 0.01 as well, but 0.1 is good enough. Comparatively smaller, because we have to take higher and higher values. So we'll have a curve like this. So the higher the frequency, increasing. As you can see in the semi-log, actually 1, then 10, then 100, then 1000. So this one will keep always going down. But this is getting saturated after some time. So we'll go in detail of this thing, how they're actually coming. So this is one way to plot it. And this is actually basically your board plot, magnitude versus log frequency, as well as phase versus your log frequency. Okay, so another plot that we are talking about is for the phasor plot. So in the phasor plot, what we are doing here is similar idea. So what is the magnitude you have to find out? So directly you find out the length as well as you find out the angle. So you put the length here. Initially the angle is 0. Okay, so if omega is 0, tan inverse 0 is 0. So 0, and magnitude initially, if the omega is 0, is 1 by half. So basically 1 by 2, that is half, is starting from here. So gradually you increase the value of omega with 0.1, 0.2, then 1, then 2. So you will have different length and different angle. So you draw according to your angle and the length. So this is how you have to draw it. Okay, so the idea is very, very simple again. So frequency response is not that complicated thing. Rather, it is a slightly math involved, but they are not complicated. But the point where what we are trying to do, so it is very, every time you have to figure out the value, then you have to plot it. So whether there is a easier way of approximating the curve without actually plotting it repeatedly, this is what we are trying to see. So for that, actually, we need asymptotic approximation of the both plots. So the separate curve that we have said, so using those curve actually, whether without drawing the, going for detailed calculation, can we approximate the lines? Okay, so sketching the board plot is simplified by straight line approximation that simplifies the evaluation of the magnitude and the phase frequency response. Okay, so we have say a general equation like this. So the first step is still same. So replacing you have to replace S equal to J omega, or you put that into the equation. Then you're going to find out the angle of this one. Okay, so sorry, the magnitude of this one. And magnitude we represent in log scale or decibel. So 20 log your magnitude G of J omega. Okay, now, so these zeros are actually multiplied together and the poles are actually divided. So in the log, what you know, that multiplication it can be replaced by addition, and the divisions are actually can be replaced by divisions can be replaced by subtraction. So basically, what is a multiplication formula? If we present in the decibel, then it becomes addition. So if we can approximate the curve for each and every one of them, okay, then we can just simply add the curves together to find out the approximate board plot. Okay, so this is about the magnitude frequency response. Now, what about the phase frequency response? Phase frequency response is similar. Okay, so similar idea because the phase is already, if it is divided, you know that it is also subtracted. So phase will also will be having a similar idea. So all the phases will be added together, okay, the zero angles, and then you have to subtract the pole angles. So I think the equation is missing here. There should be another equation for the phase as well. Okay, so now let us start with the simplified transfer function. Say that we just have a 0 at s equal to -1. So how we are going to approximate with using simple straight lines. Those straight lines are known as asymptotes. Okay, so instead of drawing a curvature, rather whether we can actually draw straight lines to plot the board diagram or not. So this is what we are trying to do. So this simple 0 gs equal to s plus a. So how we can approximate straight line for this one? So for that, the first step is always same. Let s equal to j omega. Then this is what we have. And for this one, actually we have to have normalized the value. So what does normalization actually means is that we always have to have a constant at the end. So if it is the s plus 3, then it has to be s by 3 plus 1. So always there should be 1. So if it is a higher order frequency term like s square plus 3s plus 2, so then the whole thing will be divided by 2. Okay, so to make this last column 1, so maybe it will be multiplied by 2 then. Okay, so this is what is called normalization. Actually, it helps us to find out what will be the value of the magnitude and the frequency at different conditions. So at low frequency, the value of this parameter is smaller. So this will be at low frequency it is 0. So what will be your magnitude? Magnitude will be simply A. Okay, so we can find out in the decibel 20 log m. So m is A, so 20 log A. So for low frequency. Now for high frequency, what will happen? This one will be negligible compared to this figure. So what we are going to get is A is getting cancelled out. So you just have j omega. So j omega is nothing but omega and 90 degree. J is actually shifting the magnitude by, shifting the phase by 90 degree. So you have magnitude. So magnitude is, if you apply the whole formula, so then you can write in this way, 20. So because they'll be multiplied together, these two. So 20 log this magnitude. So 20, you can say that you can directly cancel each or just say this will be your scenario. But yes, we can do that. But we actually want to figure out what will happen whenever your omega equal to A. So for that, it will be actually helpful to keep it here. So at omega equal to A, what will happen? So log, this will be 1. Okay, so what will be, we are going to have is this magnitude only. So this is what is called, this is why A is called break frequency. So it will maintain a particular value. Okay, so it will maintain a particular value up to the break point, that is omega equal to A. And whenever it is omega equal to A, then it will take a straight line approximation like this. Straight line, something like this. Okay. Let's look at the straight line approximation more clearly in the next slide. So what we have is y equal to, say y equal to our output 20 log m. Okay. So if log m is actually can be approximated, then what you can say it as x, then 20x. So this is nothing but y equal to mx. So the slope of which is 20. Okay, so this is what is called a straight line approximation, and for your magnitude, and these are also called asymptotic lines. So as you can see, at break frequency A, up to the break frequency A, it is maintaining that same magnitude as 20 log A. So after the break frequency, it has a slope of 20 decibel, 20. So now, so this 20 log with the frequency that is changing with 20, there is two ways of doing it. So one is doubling the frequency. Okay, so if you double the frequency, what will be the magnitude? So doubling the frequency means is here, if you double it, log 2, then what will be the value? So as you can see, it will be increasing with 6 dB per octave. Octave is nothing but doubling the frequency. But if it is not that convenient for us, because our semi-log graph is changing with the frequency of 10. So basically, since our normalized curve, that is why we always have A here. So 0.01, then 0.1, then A, then 10A, then 100A. So basically, we want to know how they are going to change for a change of frequency of 10 times the frequency or octave. So that is why. So 20 log 10. Okay, so 20 log 10 is nothing but log 10 is 1. So 20 decibel per decade. So for each change of 10 times the frequency, it will be changing by a 20 decibel. So whatever the value here will be 20 decibel more. Okay, so add this one compared to this one. Okay, so in the next decade as well, it will be 20 decibel. So it will be changing with a 20 decibel line. So this is for a simple pole. What will happen to the phase? Okay, so phase is also, you have to be careful whether you have noticed on the last slide or not. That is, phase is actually changing with, phase is actually changing. Initially, the phase angle was 0. Then it is, you have a phase angle of 90 degree. So initially, your magnitude was only 20. Initially, your magnitude was just A, isn't it? A. So basically A is 0 degree. And then after at high frequency, what you have seen is omega with omega 90 degrees. So basically a phase shift of 90 degree will be happening. So at break frequency, what will be the value of the phase that you have to look? Then we have to decide how to plot it. So at break frequency, that means whenever your omega equal to A. So at break frequency, whenever your omega equal to A, so what will be happening to your angle? So angle will be actually tan inverse A by A. So basically tan inverse 1, tan inverse 1. And it will give you 45 degrees. But we know that there should be a phase shift of 90 degrees, isn't it? So initially it was 0, then at high frequency it was 90 degrees. So, but at break frequency, at the middle, you have 45 degrees. So what we do actually, we take a 45 degree per decade curve. So that means we start 1 decade earlier where the phase was 0, okay? And at the break frequency, you have 45 degrees here. And after another decade, actually, we have the total phase shift, that is 90 degree. So whenever you are applying that at break frequency, it is actually at the middle of whatever the total phase shift. So for a simple 0, there is a phase shift of 90 degree. Okay, so and it will be at break frequency, it will be 45 degrees, and 10 decade before it will be 0, and 10 decade after it will be 90 degrees. So this is how you have to plot it. So if you know the break frequency, we know the break frequency, isn't it? Because from where the break frequency is coming, from the pole 0 location, isn't it? So we just figure out what is S by A, then we figure out the thing. So you know the pole location, so we know the break frequency location as well, and the break frequency gives us both the magnitude, that will be magnitude straight line that will be coming to the break frequency, then it will be increasing with the 20 dB per decade line, and for the phase angle it will be starting 1 decade before, and it will be ending 1 decade after, and a total change of 90 degrees of phase shift. Okay, and at the break frequency it will be half of it. So this is how the pole will behave. So this is a straight line approximation of your board plot for your simple 0. Okay, so here actually in the book you have a table. I haven't just bring the tables here. So actual and your approximated curve are actually plotted together, and this is the difference that we can see with the actual and the approximate. So this is a maximum error that is occurring here at this point. But it is good enough approximation, because otherwise we have to do a lot of calculation if we try to do it manually with the help of the calculator. But nowadays, since program like MATLAB is there, it is actually convenient to plot it in the MATLAB rather than doing the calculation or even doing the approximation. The point is, in the exam hall, we don't have the MATLAB. So that is why it is better for us to actually go for this asymptotic approximation. Similarly, you can also see that in the phase angle as well, uh, we have error in these areas, as well as slight error is also there. But more or less, these are actually uh, uh, better approximations for easing the calculation. So difficult calculations, so we can avoid, and you can just go for the straight line approximation or asymptotic approximation. Now, what about the pole? Pole is 1 by S plus A. You can go for the calculation again, but I'm just assuming because they're opposite to each other. So whatever the behavior that we have seen, it will be just exactly opposite. What does it mean? The previously we have seen that for the zero, there is a 20 dB per decade increase in the phase. So here the magnitude has to be 20 dB per decade decrease. Okay, so a magnitude wise, which is evident from here. Okay, and similarly, what will be the phase angle? So the zero was actually offering a phase angle of plus 90 degree. So now it has to offer a angle of minus 90 degrees since it is a zero. So similarly, you can actually go for the linear normalization, and you can figure out what should be the curve. Okay, so I'm just saying it will be exactly opposite, and you can verify that. So let us look at that one. Okay, somehow that one is not visible. Okay, let me check what happened. Okay, somehow the picture is not visible. Okay, something went wrong. Okay, so the same thing here as we have anticipated that here, as you can see here, there is a 20 dB per decade line, and as well as there is a total phase shift of minus 90 degrees. So it's starting from zero at the break frequency. We have normalized the frequency here, frequency by A. So at break frequency, we can see that there is a minus 45 degree per decade line is there. Okay, so somehow they haven't shown it. I'm not sure why last time. Okay, so now go for the next one. So pole at both plot for zero at the origin and pole at the origin. So since we don't have any starting value for them, we're just starting from here. It will always start with a 20 dB per decade increasing and decreasing line. Okay, so this is what you can see here. For a zero is always 20 dB per decade increasing line, and a phase angle as well, a constant 90 degrees. So there is no change from 0 to 90 degree because pole is 0 is at the origin. Similar thing is happening here. A decreasing line from anywhere you start, it will be always going for with a 20 dB per decade line, and also a constant phase change of minus 90 degree. Okay, so now look at this example, example 10.2, a particular transfer function given. And what they want us to do is we have to draw the dot plot for this one. So as we said already that we have to normalize the thing. So what we have done is actually we have a The transfer function is something like this, which is k s plus 3. So we have a 0 at minus 3, and then we have a 3 pole s plus 1, s plus 2. Okay, so you have to normalize them. So you take 3 out of this one, and then you'll have 3 here, and you'll have 1 here, and you have to take 2 out of here. So 2 will be there, and s by 2 will be there, and it will be 1 here. Okay, so bottom line is what we are going to get is 3 by 2k. Then you have your first order, the simple pole and 0. So s by 3 plus 1. Then you have s plus 1. Then you have s by 2 plus 1. Okay, so magnitude wise, you have to figure out what is the magnitude at the 0 frequency. So there is one variable parameter k is here. So for simplicity, we're just saying that k equal to 1. So say you want to start your curve plot for omega equal to 0.1. Okay, so omega equal to 0.1 or varies close to 0. So what will be left is only the magnitude of this one will be available. The rest of them will be, we can ignore 0 because here it is 1, 1, 1. So what we are going to get here is s is equal to 0.1. So it will be 3 by 2. K is already assumed 1 into s equal to j 0.1. So actually 3 by 2 is 1.5 divided by 0.1 will give you 15. Okay, so 15 is your magnitude, and what is angle? And j will be going upwards with a minus j, so basically minus 90 degree. Okay, so this is your starting value and starting phase. And then what about the rest of them? So rest of them, we know that zero will have a 20 dB per decade increasing line from 20 dB per decade increasing line from 3, isn't it? Break frequency is 3. So from 3, it will have an increasing line. For this one, from 1, it will have a decreasing 20 dB per decade line. For this one, from 2, it will have a decreasing 20 dB per decade line. So this is about the phase. And also we are going to see what will happen to the phase. This is about the magnitude. Then we'll also look at about the phase, how they're going to change. But we know the initial phase is going to be starting from minus 90. Okay, let's build on these ideas, how to actually plot the board diagram. Okay, so now we're considering only the magnitude. So add the contribution of table actually showing the contribution of the poles and the zeros and the total contribution at different location. This is the total, and pole at 0. We know that pole at 0 is always going to give it minus 20 dB per decade. This is what you know. And pole at minus 1 initially at lesser than 1, so it will give no, it will have no contribution. At location 1, it will start giving 20 dB per location decade. The pole at minus 2, in the first two scenario, it will have no contribution, but it will start contributing a minus 20 dB per decade at 2. What about 0 at minus 3? It will give a plus 20 dB per decade. So each and every point we have to calculate the total contribution. So only this one is contributing, so minus 20. Now this 2 is contributing minus 60 dB per decade. And here this 3 is minus 60. And because of the contribution of this one, you will have a minus 40 dB per decade. Okay, so let us draw this diagram in the log semi-log graph. So what we are going to get here, the first one is actually showing you the individual curves, individual curves. So the one that has been started here, this one, is for the pole at the origin. It is always 20 dB per decade. Okay, so you also have your constant value here, 3 by 2s. So if it is 0.1, then 3 by 2s will be log 20 log 15. Then you figure out what will be the value. Okay, and then at 1, you have a 20 dB per decade line, this one. And at 2, you have another 20 dB per decade line. And at 3, you have an increasing 20 dB per decade line. So now summarize. So initially, your value was started from this one, 20 log, this is your starting point, 20 log 15. Okay, 15, K was 1 and also omega was 0.1. For the 0.1, this is the value we are going. So this is your starting point if you plot it. Then from the very beginning, it will have a 20 dB per decade line. So it will be following a 20 dB per decade line like this, up to which point? Up to point A. So at point A, you have 20 dB per decade for this one as well as for this one. So you'll have 40 dB per decade. So how long it will continue? From the next one. So it will be continuing with the 40 dB per decade up to this point. In the next point, it will be further decreased by 60 dB per decade line. So here again, now you have a contribution of your 0. So now it will again 40 dB per decade. So this is how you sum up all the curves together to find out your magnitude board plot. So once you are familiar, actually you don't have to draw this diagram. Directly you can draw this one once you have practiced well. Now what about the phase diagram? So phase diagram, we know that the contribution, we already figured out the starting location, isn't it? We are starting from minus 90 degree. And then we have here is actually a pole at, whether you have recalled or not. So we have a pole at -1, we have a pole at -2, we have a pole at 0 at -3. So it will start at 0.1. And the effect should be finishing if it is a normal case, because we have some other pole, then the effect will be finished, will be at 10. The effect of this one should be starting at 0.2 and it will be finishing at 20, and the effect of this one will be started at 0.3 and the effect of this one will be finished at 30. So your starting points of the pole 1, starting point of the pole 2, starting point of the 0, then the ending of your pole, which there is a mistake in the book, it should be 10. So ending of the pole at -2 and ending of the 0. So what is the contribution? So contribution of the pole is minus 45 dB per decade, because we said, because we are dealing with the decade now. So total will be 90 degrees, no doubt about it, but it will be divided into 2 decades. So starting from 1 decade early and ending 1 decade late. So it will be 45 degree per decade. So at for -1, it will be starting at 0.1 and it will have a minus 45 degree per decade. So no other contribution. So total contribution is actually minus 45 degree per decade. And at 0.2, the other pole is coming into act. So it will have minus 90 dB per decade. At 0, so 0 is contributing plus 45. So one of them is getting cancelled out. So it will contribute to minus 45. So minus 45, it will continue up to from 0.3 to actually 10. So in the 10, the effect of the first one is finished. So you have only these two. So basically you have 0 angle contribution. So it will be stable there for some time. How long? Up to next one. So from 10 to 20, it will be stable. Okay, so after 20, the effect of this one is vanished. So only have 45 degrees. So it will actually increase. How long? until the effect of this one, which is finished at 30. So after that, it will be again a straight line. So let us see the diagram. Okay, so individually you can draw it initially, because initially it is difficult to understand what is happening. So initially, as you can see, the contribution of the slope because of your pole at the origin is this one, always decreasing. Sorry, yeah. Well, the pole at the origin we already taken care of. That is why we're starting from minus 90, isn't it? So now here, what we are seeing is that this is point 1. So the first pole at 1 is actually starting here, the effect of which is finishing at 10. And the next one starting at point 2, and the effect of which is finished at 20. And 0 is increasing, and it has been finished at 30. Okay, so my 1, 3 to 30. 1 decade before and 1 decade after. So now combining the all three, so minus 90 degrees from the pole at the origin. So we start with that one, minus 90 degree. Then from this point to this point, okay, so point 1 to point 2, then point 3. Okay, so point 1 to point 2, only the contribution of the pole at minus 1. So it will be 45 degree per decade. So in between point 2 to point 3, we have the contribution of minus 1 as well as minus 2. So basically, and 45, 45, so 90 degree per decade it will be. Then at this point and onwards, what you are going to see, the contribution of these two and the contribution of the 0 of this one. So one of them will be nullified. So it will continue with the 45 dB per decade until the effect of the first one is vanished. So now you have only the contribution of minus 2 and minus 3, which is opposite direction, because this is pole, this is 0. So you don't have a contribution. So this zone, it will be remaining steady value. Then the effect of this one is vanished at 20. So at 20 it has been vanished. So 20 to 30 until the vanish of the 0 at minus 3, you will have a 45 dB per decade increase. Then you have a phase will be shifting there forever. So overall phase shift that you can see is after the transition is from minus 90 degree to minus 180 degree. Okay, so this is overall phase. Okay, so this is how you have to draw the board plot for simple pole and 0. Okay, so it is not that complicated. So poles actually give a 20 dB per decade a decreasing line with a total phase shift of negative 90 degrees with a slope of 45 degree per minus 45 degree per decade. And the 0 is just the opposite. The 0 is giving a contribution of 20 dB per decade increase, as well as it will give you 90 degree phase contribution at a rate of 4 plus 45 degree per decade. So this is how you have to draw the board plot. Actually, here we are concentrating how to draw the board plot, and then later on we'll see how from these board plots or board diagrams we can figure out the stability and all other performance parameters. Okay, so but sometimes you may have complex pole as well. So what will happen to that? So for that we will just take another generalized diagram, that is generalized equation, that is s square plus twice zeta omega n s plus omega n square. So what will be the changes here? So similar thing we're going to do. So our bottom idea is to have the last term 1. This is what is called normalization. So we're keeping the last term 1. So we divide the equation by omega n square. Okay. So now at low frequency, what will happen? The frequency is low. So S value is smaller, so this should be vanished. So what will be left is omega n square, and magnitude is 0. Okay, so magnitude you can directly find. You just apply 20 log n, that will give you the magnitude here. But at high frequency, what will happen? At high frequency, S square will be dominant. So this 2 will be vanished then. Okay, so what will be omega n square, omega square getting cancelled out. So our transfer function will be becoming gs equal to s square approximately. So s square is nothing but if you place s equal to j omega, so j square omega square. So basically j square is nothing but -1, so minus omega square. This is what we are going to get. So basically angle is 180 degrees. So omega n square 180 degrees. So as you can see, total angle contribution starting from 0, it goes up to 180 degrees. So previously for first order, it was angle contribution was 90 degrees. Now for a second order, it is just the double. And also we have to look what will be the decayed line. So what will be the effect in the decayed line? So as you can see, the magnitude is omega square. So basically 20 log omega square should be there, or 2 can be coming forward. So 40 log omega. So for each 10 degrees, actually, you will have 40 dB per decayed line. So double of the previous one. Okay, so look at here. So what will happen starting from the normalized scenario, normalized case again. So starting this time normalizing, actually dividing by the omega n square, and your break frequency is actually omega n. So whenever omega equal to omega n, that is your break frequency for second order system. So from the break frequency, it will follow a 40 dB per decayed line. What about the phase at break frequency? It will be 90 degree. You can also prove it by plotting the value into the equation. So and it will start 1 decade early, and it will be ended 1 decade later. So with a, previously it was 45 degree per decade, now it will be 90 degree per decade line. Okay, so bottom line is normalizing the thing. Then you have to plot the board diagram for the zeros of the second order system with a magnitude with a 40 degrees per decade, and phase with a 90 degrees per decade. So what will happen to your poles, so second order poles, if you have? So from this one, you can easily predict what is going to happen. Magnitude will be decreased with a 40 dB per decade line, and the phase will be decreased with minus 90 dB per decade. Okay, so similar thing. But here, there is one thing you have to be careful. Okay, so at break frequency, what will be the magnitude? So at break frequency, the magnitude, there will be correction factor in your magnitude. So at break frequency, as we already say, that omega equal to omega n. So now if you put the magnitude here, this portion is getting vanished, but this will be the value that will be left, that is twice zeta omega n square. So, and if it is normalized, then omega n square getting vanished, so twice zeta. So 20 log twice zeta. So this is a correction factor in your magnitude, because for different value of zeta, what we are going to see is there is a change in your curve slightly. So that correction factor has to be added. So what we are going to get here is, look at here. For different values of zeta, we have, this is for, okay, so smaller values, the more smaller it is, we have a lesser peak. So we have our approximation that says that we go up to the breakpoint, then we take a straight line approximation, but there is a contribution of this angle, this magnitude. Okay, so this is nothing but 20 log twice zeta. So for the second order system, what is the value of the zeta? Based on that, we have to add this correction factor, this magnitude. Okay, similar thing also happening for the phase. For different value of zeta, it is actually deviates. The higher the value of the zeta, it is more, the approximation is more valid. The lower the value, so it deviates. So actually for the second order system, we have to be a bit careful to add these correction factors. Okay, so let us see with the pole, second order pole, how it looks like. We approximate, anticipated it will be exactly opposite, and the scenario is exactly the same. We have a 40 dB per decade line for the, sorry, 90 dB for 40 dB per decade line for the magnitude, and 90 dB per decade for the phase. Similar idea, inverse of the zero. Now example 10.3. So example 10.3, you have to plot a board plot for first and the second order factors. So this one, we have both of them. So we actually have to figure out the normalized factors first. So normalize both the first and the second order. Then what you are going to get is a magnitude here. That is 50 by, so after factoring out here, we are going to get 3 by 50. Okay, so then we know that we have a 0 at -1, so 0 at -1. So basically at omega equal to 2, it will start, it will have a 20 dB per decade starting line. At here, you are going to have, sorry, there is a mistake in the book, I think. It should be 3. So at 3, you will have a 20 dB per decade increasing, and at 2, you'll have a 20 dB per decade decreasing line. And at omega equal to omega n equal to, actually, omega equal to omega n equal to 5, you'll have pole. So actually 40 dB per decade line will be there at 5. Okay, at 5. These are the frequencies. So at 5, this is what we're going to get. This is 2. Okay, let us try. And beginning magnitude, we already know, isn't it? So the starting magnitude is this. So 20 log, this value will be your starting magnitude. Okay, so now look at the contribution. We're starting from 0 at 0.01. So there is no contribution of any one of the pole and the 0 there. So it will keep the same as the original magnitude. And as at 2, we have a 20 dB per decade. At 3, it will continue up to 2 to 3. So in between this gap, we will have 20 dB per decade. So in between, at 3, the other one is implemented. So it will maintain the same magnitude in between 3 to 5. And at 5, you will have a minus 40 dB per decade line. Okay. So this is individually, you can see each of them, each one of them. Okay, so this is the initial value, that is this is the initial value. I think the red color was better. So move back to that. Okay, so initial magnitude was this one, and then you at 2, you have a pole, so you have a 20 dB per decaying line, then 20 dB per increasing line at 3, and at 5, 40 dB per decade decreasing line. So what will happen here is initially it will have the magnitude because of this one. So at 2, you have decade, and that will be continuing for 3. So this is 2, 3. 2 to 3, you have a 20 dB per decade, and 3 to 5, it will actually maintain the constant because one is giving 20 dB per decade increasing line and other one is giving decreasing line. So it will remain flat here in between this zone. So after at 5 break at 5, what will happen? You will have a 40 dB per decade. So we also have to be careful about the correction factor here. So which is 20 log twice zeta. So whatever the equation that was being given to us, from that equation actually we have to find out what is the value of the zeta. So the equation that was being given to us was actually so s square plus twice s plus I think 25. Okay, so twice zeta omega n equal to 2, and you know omega n equal to 5, so you can easily find out what will be the value, and then you can have to actually add the correction factor, and then you have to just rearrange your simulation, the drawing. Okay, so this is how you have to plot the magnitude curve. Then similarly, for the phase curve as well, you have to figure out. So at 2, 3, and 5 you have. So it will start from point 2, point 3, and point 5. So these two are simple poles, first order poles. So they'll be contributing pole and 0. So pole will be plus 45, then minus 45, then 0 will be plus 45, and which will be continuing up to this value. So here you have 90-degree line, so that will be continuing up to the effect of the first one getting finished at 20, then it will be continuing up to 30, then it will be continuing up to 50. Okay, so let us draw look at that one. So individually everyone is being shown, and starting magnitude was 0 in our case because we just have that magnitude 50 by 3, so and 0 degree. So that is why we started with 0, and then at 0 will be continuing up to that value. Then you will have at point 2 you'll have a decreasing line from point 2 to point 3. Then 3 to 5 it will be continuous, then 5 it will be 90-degree per decade line. Then the effect of the first one will be vanished. So basically now you have the effect of the 0. So it will be minus 45 degrees. Then the effect of that one is again vanished, 0, effect of 0. Then again minus 90 until it is 50. At the 50, the phase shift will be completely vanished. Okay, so this is how you have to draw the for first and the second order system. If you have complex pole and 0, this is how you have to do it. So this is how to draw the board plot. Okay, so I think this should be the end because we have to start another topic, huge topic, that is Nyquist criteria. So I think we can start in the next class. I'll also try to upload the videos soon possible, inshallah.